Let's begin. Hello, everyone. Thank you for another kind of session of numerical methods. Hope you had a good weekend. Some of the group names are here. I might have missed a couple. I'm not sure, but we'll have the laminated ones definitely by next Tuesday. So you can use those until next time. Please come grab it. If you're missing your group name, I did come up with a few, like these guys, these three. So if you haven't submitted a group name, there's infinite series quad. There was the Gaussian eliminators that was taken, floating point falcons, and infinite loopers. So you can pick one of those if you don't have a group name. And I want to finish up with the nonlinear system of equations. We left off at that point last time. We did f-solve with a single nonlinear equation, and I gave this example for two nonlinear equations, which can be extended to any number of nonlinear equations. In your homework, you'll have just a system of two nonlinear equations. So we'll just do that with f-solve. And if you remember, the residual functions for those two functions were given by these equations here: half x cubed plus y minus 4x, y minus sine x, e to the minus x, etc. And just the same way you did with the single nonlinear equation, you have to define a residual function, a residual routine. And in this case, you will assume that that residual routine returns an array of residual functions. You just put them on top of each other. And the argument that comes into the residual routine is also an array containing the variables in question that you want to solve for. In this case, x and y. And they're going to be stored in whatever order you choose. So you can choose x to be var 0 and y to be var 1, or vice versa. But just be consistent, and then the system will figure that out as it works through the solution process. But once you choose on an order, stick with that order. How does it know which one is x, which one is y? It has to do with the initial conditions, right, with the initial guess. Because you're going to give the initial guess. The first initial guess is going to be for your first variable, and your second initial guess is going to be for your second variable. So if you choose to sort them as x and y, your initial guesses have to be x0 and y0. If you choose to treat them as yx, where the first entry in vars is y and the second entry you treat it as x, then your initial guess needs to be y0, x0. Yes? Vars is just an argument for the residual subroutine. In the 1D case, where you had a single unknown, that referred to the root, to the kth iteration of the root. So internally, f-solve is calling that residual function over and over again. Just like we did when we wrote the code, we call residual on xi, right? So Python is doing the same, except now it's going to do it for two roots, x and y, right? And in this case, it's going to be an array. And the order in the array is whatever you want it, but make sure your initial guess is consistent with the order you choose. Okay? And then everything will work just fine. And you can pass on your residual functions also in whatever order you want, but you stick with that order. Okay? So residual 1, residual 2, it doesn't matter if you put them R2, R1. Okay? So just like with a single nonlinear equation, you call f-solve, you give it the residual subroutine, except now the initial guess is an array of initial guesses. So in this case, we have two roots, two variables of interest, so you give it two initial guesses. So we will do this together in class. You can open up your Jupyter notebook, whatever, the one with the pipe flow or a new one. And we'll start with, let me see, I'm going to create a new notebook and move it over there. Move to Croston. Okay. And zoom in a little bit for those in the back. And I will import my boilerplate, usual boilerplate. So in this case, from NumPy, I also need cosine, sine, pi, and exponential, or just leave them as is. So from import numpy as np matplotlib inline. And from scipy.optimize, I need to import fsolve. I did not put in the magic here. Let's put in the magic for matplotlib. Okay. So the first thing I like to do, if possible, is to plot the nonlinear functions to visualize them. In this case, we are lucky because you can segregate. Let me move the window 1 second. Okay. So if you look at our two nonlinear functions, you can write them y as a function of x. Okay? If you had some crazy function on y, like cosine y or some log y, etc., you probably won't be able to just extract y as a function of x. In this case, I set up the problem so that we can actually visualize y as a function of x, so we can plot it in this way. So that's the first thing I would like to do, is to define subroutines for these two functions. The first one, this guy. So I'll define def, let me call it f1 of x, and that's going to return 0.5 times x cubed, minus 0.5 times x cubed plus 4x, right? So that's the first one of those functions. And my other function, f2 of x, is going to return np.sin x times np.exp minus x. Okay? Now, to plot those, I need an array for x. So we will do this with a linspace, x equal np.linspace. Maybe we go from minus 4 to 4. And plt.plot x f1 of x. And plt.plot x f2 of x. All right? OK. I'll give you a minute to catch up. So what I'm doing here, we're just presented with a system of two nonlinear equations. Okay? I want to get an idea of what they look like. I want to get an idea of where the roots are located. Remember, for a system of equations, finding the roots means finding the points where all of those functions intersect with each other. We are lucky here because it's just a system of two equations. So we can visualize that. Once you go to 3 or 10 or 100 equations, it's very hard to visualize in those cases. Okay? But when you can visualize, you should. And all I did here is define those functions as Python routines and plot them. And I can add a grid. So, there's a root somewhere here between like minus 3.5 and 5 maybe. There's another root over here between minus 2 and minus 1 on the x-axis, and 0 and minus 10 on the y-axis, and so on. There's a root at 0. There's another root over here. Okay? All right. So I'll let you catch up with this. Now we need to define our residual subroutine. Okay. Define residual subroutine for fsolve. Okay. So let's say def residuals. Anyway, use a creative name. And I'm going to call it vars for the argument. You can call it whatever you want, maybe roots, or it seems like vars seems to be a reserved quantity. I hope not. We'll see. And then I'm going to choose that the first entry in vars is going to correspond to my x unknown, to the unknown that's called x. So that's vars 0. I'm going to extract it out of it. And y is going to be vars 1. And now I define my residuals. So these residuals are these guys, R1 and R2. Okay? And let's call R1 equal 0.5 times x cubed plus y minus 4 times x, and R2 is equal to y minus np dot sine x times np dot exp minus x. So this subroutine, what it does is being called over and over again by fsolve. It starts with an initial guess. It brings in x and y. It evaluates R1 and R2. Remember the Newton subroutine. It's doing R over R prime, right? Some version of that in the Newton method. It's xk plus 1 is equal to xk minus R over R prime. So it's doing something like that. So it needs access to those residuals. It's just doing function evaluations over and over again. This just defines those evaluations. And you simply return this as a NumPy array. Now, np.array, and you put them as R1, R2. That's it. That's all you have to do. And now we can call fsolve. Give you probably typing too fast. Sorry, that's so. Give you a second to catch up. If you're caught up, try to call fsolve on the residual subroutine and give it some initial guess to find one of the roots. Try to be close to the root. So how about we find that root up there between minus 3 and minus 4 and between 0 and 10. So let's call fsolve residuals. And we'll give it simply a, you need two guesses here. So x0 and y0. Remember the order of the variables I chose, x and y, not y and x. So for x, my initial guess is going to be minus 4, because I think it's, well, we know it's between minus 3 and minus 4 for x. And for y, I'm going to choose 6. And if you do that, it gives you the two roots. X is minus 3.3, so there's a root here, minus 3.3 and 5.08. Right? A little bit of a zoom in here. Zoom in a little bit. You can do this for any number of equations. It becomes harder to find the initial guess, but for problems where those equations come from a physics-informed situation, like the heat transfer problem, your initial guess is usually like some average temperature. Last, if you go to the nonlinear lecture from last year, there's additional material that I've recorded last year where I solved the nonlinear heat transfer problem that I showed you last time with radiation, with like 1,000 nonlinear equations. But you don't type them up like this. You just use the formula and loop over the residuals and build in the residual array, okay, the residual functions array. You don't have to do that, but if you're interested in more, you can look up that lecture from last year. It's on YouTube, playlist for 2023 numerical methods. Okay? Don't forget to subscribe and like the videos and comment. It triggers the algorithm. Okay? All right. You can choose another route, but that's it. Frankly, I don't see you needing any more than this for the next few years. Okay? Once you hit a point where like, you're going to have these aha moments as you go. So next year is the cognitive overload in our department. You're going to do mass transfer and heat transfer and fluid mechanics and thermodynamics and crazy stuff. Okay? And you're going to use all of those tools. I hope you come back to those tools. Because those who come back, they find faster ways to do their homework and learn the material. And there will be more aha moments, things fit, these eureka moments, right? Things fitting together. I doubt you will need more than this, but this is the strategy. You can extend this to any number of nonlinear equations. Remember the residual form, okay? You're solving nonlinear equations. You're not solving residuals. The residuals is just a standard form to put everything on the left-hand side equal to 0. Okay? So we don't have to worry about constants on the right-hand side, etc. That's all I have to say about nonlinear equations, frankly. Okay? This is the last topic for the exam next week. Okay? So what we're going to talk about and for the remainder of this lecture is not going to be on your first exam. Okay? All right. So should we switch gears? Let's do it. Let's switch gears. Okay. All right. So we are done with part 2 of the course. So part 1, we did kind of this flirting with the idea of numerical methods and errors, just kind of got a lay of the land. It wasn't much of a unit, but let's call it part 1. Part 2 was solving equations, algebraic equations, linear and nonlinear. Okay? Part 3, you would imagine solving differential equations, but unfortunately we need a little bit more work before we get to solving differential equations. So we're going to squeeze in between solving algebraic equations and solving differential equations. We're going to squeeze in a unit called curve fitting or data analysis. Okay? If you've done statistics, this is going to complement that work. Once I hit regression after this chapter, there's going to be a lot of things clicking in your mind, especially if you've taken statistics. Okay? So the idea of curve fitting is that you have data, and you want to represent this data in a unified form. Okay? I'll start with a few examples. First, with the learning objectives that you will learn, define what it means to interpolate data. You will derive the system of equations that one needs to solve to build what we call a polynomial interpolant. You list the benefits and limitations of first-order interpolants, benefits and limitations of high-order interpolants, polynomial interpolants. Calculate by hand an interpolated value using linear interpolation, blah, blah. Identify which points are best to use for a linear or a quadratic or a cubic interpolant. List the conditions for cubic splines. You've probably heard of splines, or maybe if you've done like Adobe drawings, etc., there's an option where you select splines. We will learn the math behind splines and how they're built and why they are super, super amazing and useful. You'll just be responsible to list the conditions because the derivation and the math is very tedious and complicated, but the conditions are easy to understand and comprehend, so you'll only be responsible at listing the conditions. We will be using built-in functions, although we can do all of this with the tools that we have, because you will see all of the interpolation we're going to be looking at boils down to either linear systems of equations or nonlinear systems of equations. That's why we study those at the beginning. Okay? So you will see to build an interpolant, you need to solve a system of linear equations. Okay? At the end, if we have time, we'll show how linear interpolation works in 2 dimensions. So you'd have 2-dimensional data like pressure and density, for example, and you want to find somewhere in the middle between like 4 data points. We'll learn how to do interpolation in 2D. 3D, it becomes more complicated, but the concepts are similar. You'll learn how to do it in Python as well. Then, if we have time, in red here is how we do linear interpolation with arbitrary basis functions and nonlinear interpolation, which almost nobody does, but it does set the stage for nonlinear regression, which we will cover next. So you can see now curve fitting is going to have interpolation and regression. Regression is something entirely different than interpolation. And as I talk through this, it will start making more sense to you. So the motivation is that, I wish I had a video for it was hard to find some nerdy discussion about interpolation in a film or a movie. If you know of something like that, please send it to me so I can put it and tell my story. But for this chapter, I don't have a motivating film. So we'll just go through the text. And so you often have discrete data. Like I will show you next. I measured the temperature at my home in August, and you have discrete data points, like my thermometer measures like every hour, and I wanted to get the temperature between 2 hours, right? So how do you do that? You do what's called interpolation. You kind of know how to do this. We're going to just put a mathematical umbrella around it. So the idea is that you have data discretely collected from experiments, because you're sampling at a given interval. You're not sampling continuously. Sometimes devices sometimes there are limitations in the devices to measure continuously. Sometimes it just physically is meaningless to measure continuously. So you cannot have a nice curve. You have these discrete data at different intervals during the day. Or let's say you want to measure the temperature in this room. You could put a sensor here and a sensor there, but those are just two sensors in this big room. So what about the temperature in between or on the sides, right? So you often do not have a full representation of data, especially if it's drawn experimentally. You only have it discretely. The concept is we take those data and we fit, well, I don't want to use the word fit. We pass or we weave a polynomial function throughout those data points. Now, why do we choose polynomials? I'm going to go on a little segue here. If you're mathematically inclined, you'll enjoy this. But if you're not, this is something that is useful. The mathematicians say that the function space of all functions in the world, sines and cosines and logarithms and exponentials, etc., that entire space, it is filled with polynomials. Every point you pick in the xy plane, you are guaranteed to find a polynomial, so x squared plus alpha x cubed plus beta x to the 4, etc. You are guaranteed, it's a theorem, to find a polynomial that passes through that point. You're not guaranteed to find a cosine or a sine function or an exponential, but you're guaranteed to find a polynomial. In fact, when you look at the Taylor series, all functions are expressed as polynomials, right? That's what we use in calculators, right? So that's why we like polynomials, because they are dense in the function space. Any set of data you're given, you're guaranteed to be able to pass one or more polynomials through those data. So we're going to use that to our advantage. We will take those points and say we're going to weave a polynomial through the data. We're just going to connect the dots, though. Okay? We're going to connect the dots. It's technically, I know I have it here. I have the word fit the data, and I'm going to remove that. It's technically incorrect to say fitting. Interpolation is not data fitting. Interpolation is simply weaving something through a bunch of data points. And we'll cover that through when we hit regression. Then, now that polynomial, you don't know what it is. Is it 2x squared plus 3x cubed minus 4x to the 5th? Or what are the coefficients, right? We don't know the coefficients. We are going to solve for those coefficients. So we're going to say we have data points. Let's weave a polynomial through them of some order, and let's solve for the coefficients. We will learn in these lectures how to find those coefficients. Okay? Then, once you have that representation, it's a formula. Then you can take it and apply it anywhere. So let's give an example. This is the temperature data one day in August at our home, my home, from midnight, so 24 hours. Okay? So starting, let's see. Okay, 1, 2, 12. Okay, so this is so this is the afternoon. Okay, all the way to midnight, starting in the morning. Okay, so you see in the morning hours, right? It gets down. Then the sun rises around here, 6 o'clock in the morning, and then starts warming up. Right? Temperature climbs. The hottest time of the day is not noon. It's actually kind of 2 or 3 o'clock. Right? So. And you learn that when you plan activities with your kids. You're like, oh, we better go to the park before 3 o'clock because we're going to be roasted, right? On that day, it was around 4 o'clock, kind of peak temperature. And then, the sun, goes down, starts setting, and then it cools off. So this is the temperature cycle, and it repeats. It repeats, okay, every day. All right, so then if I were to ask you, what is the temperature at 1 o'clock? So I know the temperature at 12 noon and at 2 o'clock. What is the temperature at 1 o'clock? Give me a guess. Numerical ninjas. 87. How did you get that number? Between the two? Right? Yeah? That's a great guess, right? In the absence of any other knowledge, this is the best guess you could do. Right? So your colleague is saying that, hey, 1 o'clock happens to be exactly at the midpoint between 12 and 2. Right? 1 p.m. is exactly between 12 and 2. So it's right in the middle. So we're just going to take the average between these 2 points. So 89 plus 86 over 2. Right? Is that what you did? Okay. It's actually 87.5. So if you take that average, that's kind of the best guess, right? Just an average. Okay. So now, what is the temperature at 1:17 p.m.? So that's 13.28 hours. So if you're counting on the x-axis in terms of a continuous hour, 24-hour clock, at 12 you have 86, at 14 you have 89. What is the temperature at 13.28? Just describe how you would do it.
I would take those 2 points of 86 and 89. I find the slope between them, and then I use that slope to create a line. That would then I can plug in 13.28 hours.
Okay. Okay, great answer from mediocre at best. So that's one of the groups we have. Okay, what do you think? What do you think? Do you have another idea? Do you have another idea? No? Yes? So what they did, they just drew a straight line between 86 and 89. So we only have 2 points. There's nothing in between. So the best thing I could do with 2 points is draw a straight line. So they drew a straight line, and they intersected the straight line with that vertical black line. And they found that intersection shown here in this kind of blue triangle, right? Simple, totally legit. Okay, so draw a straight line intersected at 13.28. Okay, now go ahead and do that. Grab your papers. Okay, find me that equation for the straight line and evaluate it at that point. So find the slope of the line, find the intercept, and evaluate it at 13.28. Want to pick one of these funny names for your group? Did you send me a group name? No. Okay, so you can pick one of those. This one? Okay. Okay. And I didn't print your name. That's right. What was your?
It's various variables.
Various variables. That's right. Thank you. Yes. Yes, you're right. You're right. So are you guys in a group, Michaela? And okay, you're with them. Okay, and okay, you're with the funny name here, and you're the 264833719. And so are you not with a group? No, you don't want to be with a group. Okay. 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 So you drive. Okay. Okay. Okay, so where are we at with the crazy straight line formula? You can at least find the slope. Find the equation for a straight line between 2 points. I'm hoping they still teach that in high school these days. There's been big changes to the math curriculum. All right. Do you have some answers? All right. Okay? Bernoulli babes? No answer? Same? That's a smart answer. What was that number again? It is okay. All right, so let's see. All right, so we draw a straight line. The equation for a straight line is mx plus b. I use m for the slope, okay? T is the temperature, so I'm going to call this equation for the straight line T of x, right? And x is the hour of day. The slope is simple. It's a straight line, so it's a simple rise over run. 89 minus 86 over 14 minus 12. That gives you a slope of 1.5. And then to find b, the intercept, you evaluate that equation at either one of those endpoints, either at 86 or at 89. So t at 12 needs to be equal to 86 because that straight line has to pass through 86, or t at 14 needs to be equal to 89. Either one of those is going to give you that same value for the intercept. So I'll choose the left point. T at 12 is equal to 86, which is equal to m times 12. So this is the x value, right, the hour. M is the slope 1.5 plus b, gives me 18 plus b. And then I can solve for the intercept, which turned out to be 68. So I have my equation for that line between those 2 points, only between those 2 points. It's 1.5x plus 68. And finally, you evaluate the temperature at the desired hour, which is 13.28, and you get 87.92 degrees. Okay? So now, this is an approximation that gives us the values of the temperature. Okay, but between what points? Where is this valid? Is this valid at 11 o'clock? Is this valid at 4 o'clock in the afternoon? Where is this valid? Yeah, between 12 and 2. Just between 12 and 2. You go outside, you're going to get something different. That's why it's called interpolation. So those 2 points at the end, they bound the limitations of your knowledge. You don't have knowledge outside those points. At best, between those 2 points, this is the best you can guess. Now, it could be that the temperature doesn't vary as a straight line between those 2 points, but it's still in the absence of any other information, this is one of the best guesses you could take at what's happening between those 2 points. If those 2 points were closer to each other, let's say you sampled the temperature at 12 and then at 12:10, right? That's even better. You're kind of tightening that interval. Now what you did is it's called linear interpolation. Okay? You know how to do this. And now all I'm helping you do is formalize it and push your knowledge a little further. So let's generalize. I will give you, given 2 points, this is in general, 2 points, x and y pairs. X refers to the independent variable, like the hour of day, okay? And y refers to the dependent variable, the temperature as the function of hour and day. So typically your data is obtained as x and y pairs. For 12 o'clock, temperature was 87. For 2 o'clock, temperature was 89, right? So those are x, y pairs. So in this case, I have 2 pairs, x1, y1, x2, y2. And I'd like to fit a straight line between those 2 points. The equation for this straight line is mx plus b. What are my unknowns here? In red, m and b, the slope and the intercept, not the x values or the y values. Because I know the x1, y1, and x2, y2. I'm trying to build an interpolant between them, a straight line interpolant. For that straight line, my unknowns are the slope and the intercept. That's it. The coefficients of that straight line. And by definition, an interpolant, by definition, must be weaved through each of the data points. So it must pass through each data point. If you've taken statistics, or if you've done a best line fit in Excel or in Pandas or whatever, you will find that the regression line doesn't pass through each and every data point because it's not interpolation, it's regression. It's something different. Here we are doing interpolation. We at least must recover the original data. So if I were to evaluate that straight line at x1, it better give me y1. If I were to evaluate it at x2, it should give me y2 by definition, by construction, right? So how do you do this? Well, you pass this point. You have two variables, two unknowns, m and b. You need two equations. Well, if you pass, we just said it, that this line should pass through x1, y1, x2, y2. Those are our equations. At x1, this straight line should be equal to y1. So there you go. y1 equal mx1 plus b. That's my first equation. My second equation is that this line should pass through x2 and y2. So at y2, that's equal to mx2 plus b. Two equations and two unknowns. It's a miracle. Now, what is that? That's a linear system of equations in m and b, in the coefficients, not in x and y. Previously, we were writing ax plus ax1 plus a1 x1 plus a2 x2 and so on, and we put x as the solution vector. Here we've swapped things. x1 and y1 are known values. The coefficients are unknown in this case. So this is a system of linear equations in the coefficients of that straight line. You write this in matrix form because it standardizes things, it beautifies it. And there you go. This is, you solve this and you get in one shot the slope and the intercept. We did it by hand manually, right? But you can invert this system and get the exact solution for that for any case. So now you can solve for m and b and substitute, and you get this general equation, okay? So the slope is y2 minus y1 over x2 minus x1, right? That's the slope, right? And the intercept is some kind of, I rearrange things a little bit. So now with this equation for general straight line interpolation, given x1, y1, x2, y, given two data pairs, x1, y1, x2, y2, you plug in those x1, y1, x2, y2 into this equation. You plug in an unknown, the desired value for x, and you'll get the value of y that you desire. Okay? So in the temperature and hour of day example, x1 was what, 87, x1 was 12 o'clock, x2 was 2 o'clock, y1 was 87, 86, y2 was 89, and x, the unknown, was 13.28 hours, right? And y was the temperature value. Okay? This is super easy to use. Homework, exams, you're flying on an airplane and you want to solve, the world problems or something, you do linear interpolation, right? The disadvantages is it's not very accurate if the data is really nonlinear. Okay? So we don't know between these 2 points if the data is actually like this or like that, right? What do you do in that case? If you know nothing else, maybe a straight line is your best guess, right? But if you know that the behavior is not a straight line, we will learn how to do something else in between those 2 points. Okay? Okay. Now, for a larger data set, you can also achieve linear interpolation and do it for the entire data set. This is an example of the density of air as a function of temperature. So the lower the temperature, the heavier the air is, right? It gets denser and denser. So at 100 Kelvin, the density of air is almost 3.5 kilograms per cubic meter. And as you heat the air, 1,000, temperature density drops to almost a half kilograms per cubic meter. But you see kind of this nonlinear trend in the data. But you can apply linear interpolation to those data. So what do? Do you draw a line from the first point to the last point? No. You take each pair of 2 points at a time and draw a straight line in between them. So you connect each pair of points with a straight line. Okay? So if you were to zoom in here, this is what this looks like. Okay. Now, if I were to give you this data, and ask you to find me a value between some 2 points. What would you do in Python? It's a nightmare. You have to search, find where your point of interest is between which 2 points, draw that straight line between those 2 points, or develop the equation and find the formula. It's kind of annoying. Okay? Well, thankfully, Python does that for you behind the scenes with like 1 line of code. Okay? So let me introduce to you the function interp. Okay? So the function interp is our basic 1D interpolation for straight lines in Python. And it takes 3 arguments and returns a single value. Okay? It's within NumPy. It will be cool at the end of the semester to summarize all the kind of routines in Python that we use and give you a handout for your future courses. So it would be a good idea this year to do this year. Okay, so going back to interp, the arguments for interp, let's start with xe. Xe is the value at which you want to interpolate the data. Your data is given by xi and yi. Why I chose I chose I as input. Those are the data that you provided. Okay, so that's temperature versus hour of day. Okay, or density versus temperature. Right? X values, Y values. Those are discrete points. 10 points for X, 10 points for Y. 50 points for X, 50 points for Y. You give it all of those data, and you tell it, find me the value at any point xe between those data. It will find the pair that matters, do the linear interpolation, and return a value in ye. Okay? All right, so let's do this together. Go on in Canvas under modules. There's a module called interpolation. And there's a notebook there called interp activity 1 with gaps. Okay? So go download that one and load it up, and we'll work together through it. It contains the data for the density versus temperature. All right. So it should look like this. Interpolation coding activity 1 contains a bunch of things already preloaded. Give you a minute to load that up. And you see I have temperature and density data already pre-programmed for you. Typically, you would import those from Excel sheets or data files. I'm not going to worry about that now. I'm sure you know how to do it with pandas, all right? So if you have that notebook, this is what you should see. Agreed? Okay. So the first cell is just the boilerplate. I'm just going to go ahead and execute it. And the next cell contains the temperature and density array. And as you can see, the temperature array, I created that with a lint space, 100, 150, 200, and so on. Okay. Now, you know my rule of thumb, when in doubt, print it out. My next rule of thumb, when data is at hand, plot it to understand. So I used GPT to help me come up with that one. Okay? So we used to say when you're presented with data, flirt with it, plot it, etc. I think it sounds nicer when we say when data is at hand, plot it to understand. So the first thing you do, always, 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 you have data, just plot it to see what it does, what it's doing. Okay? Plot it in all sorts of ways. If it's multidimensional, take each dimension at a time. Okay, and plot the data to see what it does, to get a feel of it, get a sense of what it's doing. All right, so let's go ahead and plot these data. So I have a couple question marks here for you to fill in the gaps. So go ahead. We want to plot density as a function of temperature. So you have an array for temperature, array for density. Go ahead and fill in the gaps. So the temperature array is T. The density array is rho, \rho. So on the x-axis, I want to put T. On the y-axis, I want to put rho, \rho. And when I execute this, I get this beautiful, nice-looking plot. Agreed? OK. Now, again, when you are presented with discrete data, plot it as a scatter. Do not connect it with a line. Why? When you ask Python to connect the data with a line, you are actually telling Python that to linearly interpolate the data, to draw a straight line between those data. Let me show you. So I'm going to take that same plot now, and I'm going to do T and rho. I'm going to do K, O, dash. Look what it did. It connected the dots with a straight line, right? And that's not necessarily true. That will give you the illusion that your data is continuous. It's not. It's a scattered data. If you insist on connecting them with lines, make sure you put circles or symbols on them to strengthen the idea that your data is discrete, not continuous. Make sense? There are cases where I could show you if you draw a straight line, it will completely blind you from visualizing the data. I can take two sine functions and shift them by like half a radian, okay, or like 25 degrees. And you connect the dots, you're going to get something like this. Whereas if you don't connect the dots, you'll see the two patterns of two sine functions. Don't connect the dots. Scatter data is scatter data. Plot it as symbols. If you insist on connecting them with a line, keep the symbols, okay? Now, this is actually what linear interpolation looks like. That's what Python is doing, is drawing a straight line between each pair of points. All right, so now we're going to start probing the data. OK, so you plotted it. You got a feel of it. The temperature, the density decreases with increasing temperature. The data makes sense. There's no outliers, right? If at this point you saw a sudden spike in density, that's probably an error with the apparatus. You discard that data point. You throw it away. Okay? So it's important to visualize your data first. See if it makes sense. OK, so now we will use the numpy's interp function to find the density at t equal 132 degrees. OK, Kelvin. This should be Kelvin. Sorry. OK. So you probably don't remember what the interp function does. So the interp function, the last two arguments are the input data, the input x values and the input y values. The input independent variable, the input dependent variable. My independent variable in this case is the temperature, and my dependent variable is the density. So I'm going to give Python those data. Now I need to find the dependent variable rho at a temperature of 132. So I put 132 over here. Look at that, 2.775 kilograms per cubic meter. Okay. Now does this make sense? Does this make sense? Well, let's see. At 132, we are somewhere here, right? And it's giving me 2.7. So yeah, that makes sense. It is within those data points. So, and I can verify that. I can actually plot that point on top of this. Okay? Let's go ahead and plot that value. Let me see how I can do it nicely. Okay. Let's go to the next one, actually. This will make more sense. OK. So now, because we'll do it over many points. So now, the goal is to find the density at several values of the temperature, 123, 251, 443, 599, 602, and 899. using numpy interps function. Now, I didn't tell you anything about whether in the interp function you need to provide a single value or an array. What if you provide an array of values to interp? It actually is going to return the interpolated values at all of those points. So it not only works for a single value of 132, if we give it an array of 132 to 51, whatever, it will return the interpolated values at those points. So let's go ahead and do that. I can do a numpy array or just a list of, let me copy those values here. Okay. And then give it xe and t and row. Remember, the first argument is where we are trying to find the temperature, the density, at what temperatures we're trying to find the densities. The second argument is the input x values, or the temperatures in this case. It's an array of temperatures. The last argument is the y values, or the densities. Okay? So now, my prediction is that this will return the density at each one of those temperatures. It will return an array of densities at each one of those temperatures. Look at that. It returned 2.99, 1.3, 0.7, etc. This is the density at that temperature. This is the density at that temperature. This is the density at 443, density at 599, density at 602, density at 899. And it looks correct because the density is decreasing with increasing temperature values. Agreed? So now, I kind of mentioned this earlier. So now let's actually visualize this on top of the original data, okay? So that you can see that it's actually doing a linear interpolation between each pair of points. So what I will do, I will take these xe values and ye values and plot them as squares, as red squares on the original data, right? So I'm going to take this original data and plot the squares corresponding to the interpolated value. So what I will do is xe and ye here. So I'm plotting xe and ye. Those are the data that we interpolated at as red squares on the original plot. Look at that. Now this makes it clearer, right? Because that first temperature was what, 123, and the density was about 2.9, right? And so on and so forth. And you will notice that each one of those red squares falls within an interval, and Python, the interp function, internally figured out which 2 points to choose to do the interpolation. For this point, it chose those 2 points. For this guy, it chose those 2 points. It didn't choose these 2 or these 2 or these 2. It chose those 2. You want to straddle the point in question. Otherwise, it's not interpolation. It's extrapolation. It doesn't work. You'd be lucky if it works with going outside the bounds of your data. OK. So now, I want to create a very dense representation of these data. Okay? So instead of interpolating to 123, 52, whatever, 522, etc., I want to interpolate at 100, 101, 102, 103, 104, 105 to create like a very dense interpolation. Okay? So simple. You can do this with a lint space. So what I'm saying here, create a lint space of 100 points for the temperature, interpolate the data to those points, and plot the data on top of the original data. Very simple. I'm going to create a lint space now from the minimum to the maximum temperature. Okay, now what is the minimum temperature? It was 100, and the maximum temperature was 1,000. Or you can take min T or max T, because you don't want to go outside the bounds of those temperature values, 100 to 1,000. Just creating a sequence of equally spaced points. Then I'll simply evaluate the density at those points and plot, and look what happens. You're not creating a new knowledge, because all of those points that we interpolated in between, they fall on that straight line. You could put 1,000 points, interpolate to those 1,000 points. You're not going to improve the quality of the data. It's still a straight line between the data. You can't create new knowledge without bringing in new data, new information. Okay? All right. Okay, so now, we decided that the temperature was our independent variable and the density was our dependent variable. But it's also completely legit to say, what is the temperature of the air if the density is 0.5 kilograms per cubic meter? Or what is the density of the air if the temperature, what is the temperature of the air if the density is 2 kilograms per cubic meter? That's completely legit as well. So if you think about the equation of state, P, rho, RT, you can swap those variables any way you like, right? We chose T and rho as, we chose T to be the independent variable because that's how we ran the experiment. But we could totally do a reverse interpolation in this case. Reverse, saying I'm going to swap the meaning of T and rho. So now I want to find the opposite. I want to find the temperature given a density. So I'm going to swap T and rho. Independent, I'm going to make rho my independent variable and T my dependent variable. All right, so here's the question. Find the temperature at which the density of air at atmospheric pressure is rho equal 2.3364. The tabulated data, we know that T is equal 150 at that density. So if I were to go up here for the original data, there's a point here at 150. T is equal to about whatever, 2.344 or something, okay? So I know the temperature for the density equal 2.334, the temperature is exactly 150. I know that from the data I collected, right? Okay, so let's try it. So we want now to swap the meaning of T and rho. So my independent variable now is rho. And my dependent variable is T. And I'm going to find the temperature at which the air density is T, 2.3364. Run it. What did you get? 1,000? Yeah. 1,000. That's weird. That's very weird. So what happened here? It's what? I'm not going to tell you. Okay. It's a little technicality. It's a little technicality. For linear interpolation to work correctly, especially when using a routine like interp, the data needs to be sorted from small to large, or from large to small, but it needs to be sorted. The independent variables need to be sorted, okay? They need to be sorted correctly, actually from small to large. The values of the independent variable need to be sorted. Now, we can easily sort data in Python. I have a slide on that, okay, that explains it after this, but let me actually show that slide. 1 second. If I can find my slides. You need to sort the data. The independent variable need to be sorted in increasing order. There are 3 ways to sort an array in Python. If you are just concerned about sorting a single array, one array, you just want to sort those values, and that's it. You have a list of grades, for example, or a list of GPAs, or whatever. You just want to sort that one array. You just use one of those 2 functions, np.sort, which sorts the array in increasing order, or np.flip upside down, flip UD. Now, flip UD, the array has to be sorted one way or the other to flip it. So if it's sorted by decreasing order, you flip it. Now it's sorted by increasing order. Okay. np.sort sorts a single array. Okay. But in our case, we need to sort the density or flip it, right? Because it's already coming in decreasing order, our data. So I need to sort it or flip it. But I also need to sort the temperature according to the sorting of the density. So if I sort the density, I also need to sort the temperature accordingly. The best way to do it is with this routine, with this Python function. This is the most general. It's called argsort. Argsort is short for argument sort. If you call it on an array, it gives you the indices that would make the array sorted. Now, why is this useful? And what does mean gives you the indices that make the array sorted? So let's say you have, in entry 0, you have 100. In entry 2, you have 50. In entry 3, you have 300. Argsort would tell you this array will be sorted if you move entry 2 to become entry 0, if you move entry 0 to become entry 2, and if you leave the last entry the same. That's what argsort does. It gives you those indices, the sorting index. But this is useful because I can take that argument sort and now apply it to any other array that is related to my first array. So I'm sorting the density here. If I get the argument sort for the density, then I can use those arguments to sort the temperature the same way I'm sorting the density, not in a different way. It needs to be one-to-one consistent. Okay? So I'll give you an example in Python. Let's say you have np, let's say you have an array A, np.array. Let's say you have 100, 50, and 300. Okay? And then I say np.argsort A. Okay, look what it did. So we know in this array, to sort it, I need to move 50 to put it here, 100 put it here, and then 300 keep it where it is. It's giving me the indices. It's telling me that the first entry should be index 1, the second entry should be index 0 in this original array, and the third entry should be untouched. Now I can use these arguments to sort A very simply by doing the following. So if I call this sort IDX or sorted indices, then I can say A of sort IDX, and it will sort it. It's brilliant the way they designed it. You gotta remember a few things, but once you get the grasp of it, this is super powerful. Knowing the indices of sorting, now I can apply those indices to any other array that's related to A. Make sense? So here's how we use it with the temperature. So first, I argsort the density. So I'm going to put this up here. Okay, and then print it, print IDX. So to sort the density, it's really, because the density was in decreasing order, to sort it, it's going to flip it. So it's going to give me the opposite order for the density. But in practice, this might not be the case. Your data might be all over the place. It might not be sorted in any order. It just so happened here that I'm sorting it in a specific way. So now I can sort once I have this sorting index, I can use it to sort the density. So row sorted is row IDX. So if I print row sorted, now it's going to be in the correct order. If you print the original density, it was started high and ended low, right? Now we sorted it. Okay, now finally, I need to also sort the temperature. It doesn't need a special order of the temperature. It just needs to be consistent with the order of the density sorting. So I just apply T to IDX, okay? And it will sort the density. And now I can use the new sorted density with the new temperature, and now I get 150 as was expected and as needed. Okay? You only need to sort whatever you're treating as your independent variable. And the sorting needs to be in increasing order from small to large. Okay? This is one of the best tricks you could use to manipulate arrays. Okay? All right. All right, let's take 4 minutes. All right, let's resume. Okay, the next question to ask is, okay, if you chose 2 data points to draw a straight line, could you choose 3 points and put a quadratic, or 4 points and put a cubic, and so on and so forth? This is exactly what we're going to do next. But first, let's formalize our definition for what we did with the straight line, where we insisted that the line goes through those points. It must go through those 2 points. And we use that fact to derive the governing equations for m and b, right? So by definition, an interpolating function, by definition, must pass through each and every point of the input data. So when we were given 2 points, x1, y1, x2, y2, with a straight line, a0 plus a1x, now I'm changing the nomenclature, m and b, to a0 and a1 to standardize the nomenclature. Then we passed this straight line through x1, y1, and through x2, y2. We applied it there. We derived a system of equations for the unknowns, which are the coefficients. So now given 3 points, x1, y1, x2, y2, x3, y3, so you could potentially have 3 equations. So therefore, you could put a function with 3 unknowns in it, right? So how about we fit a quadratic? a0 plus a1x plus a2x squared. The unknowns are not the x values. Okay? The unknowns are the coefficients shown in red. So now, given these 3 data points, I want you to write the equations that if we solve, we can find a0, a1, and a2. So I will need 3 equations, right? Because I have 3 unknowns. Definition, this quadratic needs to pass through each and every point. x1, y1, x2, y2, x3, y3. Try it individually as a group, but please try it. So for the straight line, we pass the straight lines through x1, y1, x2, y2. Now we have 3 points. We have 3 unknowns, 1 quadratic. Pass it through each one of those points. You have 3 unknowns. You need 3 equations. You have those 3 points, right? Just write down the 3 equations. Oh, you also wrote it in matrix form. Don't write it in matrix form. If you wrote it, that's okay. If you can. All right, root rascals, do you have a first equation? Can you give it to me? Okay, I agree. So the first equation you obtain by passing the quadratic, which is shown here in the red line, through the first point. So at x1, you need to get y1, and that's equal to a0 plus a1x1 plus a2x1 squared. Okay, let's see. Various variables. Do you have equation 2? So you cannot be called upon. Okay, 264-83719. Is there a phone number or something? Do you have equation 2?
We didn't get anything, but I guess A0 plus A2x, or A1x x2
Uh-huh.
plus A2x squared.
Yes, equals to? Yes. It's not that hard, right? You pass that function through x2 and y2. So that gives you y2 is a0 plus a1 x2 plus a2 x2 squared. Notice, what are the unknowns here? They're the coefficients. Okay, they're the coefficients. Last equation, the Gaussian eliminators. Do you have an equation for me? For this course, not another course. Oh, I put it up. Never mind. I have the answer for you. I have the answer for you. It's y3 equal. So again, you apply that formula for the so think of that curve that we're interpolating as a model for the data. So we're applying that model at that last point. Y3 is a0 plus a1 x3 plus a2 x3 squared. Okay? Okay, great. Those are the three equations with the three unknowns that we need to solve to obtain these unknown coefficients. Now, is this a system of linear equations or not? Okay, why not? Why are they not linear? Okay, but okay, so that, okay, but x1.
X squared is a constant value that we know, and so these variables are only showing up to the first order.
Okay, so x1, x2, x3, you're right, they show up as squared, right? So that might give you the impression that it's a nonlinear equation. But it's not, because x1, x2, x3 are just numbers. They're values. They're constants. The unknowns are shown in red, and they show up linearly. That's why when you see an equation or a system of equations, like I mentioned when we talked about nonlinear equations, are these equations linear or nonlinear in A0, A1, and A2? They are linear in A1, A0, and A2. And those are the variables in question that I care about. I don't care about x1, x2, and x3. For all I know, they're going to be given to us. In this problem, the unknowns are A0, A1, A2, and they show up linearly. So indeed, this is a system of linear equations. Just the same way that with a straight line, we had two equations, two unknowns, linear. For a quadratic, you have also a system of three equations, three unknowns that are linear. Now you can see a pattern. For 2 points, you fit a straight line with a model of a0 plus a1x. For 3 points, you can fit a quadratic with a model a0 plus a1x plus a2x squared. The unknowns are the coefficients, not the x values. The x values are going to be based on the input data. Now with 4 points, you could put a cubic. You have more equations. You could blend in more unknowns. So you could add one more term and go to x cubed. No, so now you have a 3x cubed. And you know what? The sky is the limit. For n plus 1 points, you can put an nth order polynomial to interpolate the data. So for n plus 1 points, you put an nth order polynomial. Why nth order? Because you have n plus 1 unknowns. Remember the a0. So a0, a1 through an are n plus 1 unknowns. N plus 1 points, n plus 1 equations. So think of it this way. A0, A1 through AN are n plus 1 unknowns. So you have n plus 1 unknowns. You need n plus 1 equations. Or in other words, n plus 1 points. Why? Because you are weaving that polynomial through each and every point. It must pass through each and every point. Those are the conditions that give you the governing equations for the unknown coefficients. Okay? And with that, you could say for n plus 1 data points, you can fit a general full polynomial of order n at most. Again, it must pass through each and every point. And I have 45 seconds. I can at least give you the system of equations. It's very generic. It's just an expansion of, remember, for a straight line, we had one x1 and one x2. For a quadratic, we had 1x1, x1 squared until x3. For a cubic, you'd have 1x1, x1 squared, x1 cubed, all the way down. It's a square matrix, okay? All the way to an nth order polynomial, all right? You solve this system of equations, you get the coefficients, you plug in the coefficients of the polynomial, and you evaluate anywhere you want, all right? Thank you. We'll see you on Thursday, okay? Please try to get me the feedback on the nonlinear solvers by tomorrow so I can cover it on Thursday as a Q&A, okay? Thank you.